Okay, so today we're going to talk about 2.3 in this section. And in this section, one of the first things we need to talk about is even and odd functions. So even and odd functions are basically types of functions that have a certain style of behavior. And it also kind of, in Calculus 1, we use it sometimes to talk about symmetry of shapes. Comes in handy in all kinds of applications of integration. So a function is considered even if for every x in its domain, the number negative x is also in the domain. But the big part that you guys really need to pay attention to is this. This basically says that if you take negative x and plug it into the function, you get back the same exact function you started with. That's what makes it an even function. Also, even functions are symmetric with respect to the y-axis. For me, I always think of the basic parabola y equals x squared. If you folded that over the y-axis, you would get the graph to land right on top of itself, right? So if you have something like this, and you have a parabola like right here, right? If I were to fold it that way, right over, like a piece of paper right on the y-axis, we would get a graph that landed right on top of itself. That's because it's an even function and it has symmetry with respect to the y-axis. So a function is considered odd if for every number x in its domain, blah, 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 blah. It's also in the domain. You guys get it. We just said that last time. But again, the big takeaway this time for odd is that when you plug negative x in, you get a negative version of the function. So you can literally factor out a negative. It's very important that you understand. It's not just that there's an extra negative, it's that you can factor out a negative and it will be the exact same function, but with a negative in front. Odd functions have symmetry with respect to the origin. So respect to the origin, basically the way I think of it is you fold it twice. You fold it once over the x-axis and then you fold it another time over the, you fold it once over the y-axis and then you fold it another time over the x-axis or vice versa. Okay, so it's a double fold. So if we look at this problem, if we folded this right over this y-axis right here, if we folded it right over that, would it land on top of itself? And again, excuse my drawing, it's not perfect. So yes, or not yes, it would do that. So this is an even function because it has symmetry with respect to the y-axis. Now let's look at this graph. What if you folded this guy over the y-axis? Well, wouldn't it just come over here? It wouldn't land on top of itself. So this does not have symmetry. So not all parabolas are symmetric with respect to the y-axis. Only the y equals x squared, or versions of that, of the parent function y equals x squared. So what we have is a odd, I'm sorry, this is neither. This is neither odd nor even. It's not an even function, it's not an odd function. It still has symmetry, but it has symmetry with respect to this axis of symmetry. So this is what we'll talk about in the next section. We have an axis of symmetry, but it's not an even or odd function. It still has symmetry, but not the kind we were looking for. It's very specific symmetry. Now this one's kind of hard to visualize because my drawing's not perfect, but imagine for a second you folded it over this way and then you fold it over this axis. So you fold it once over the y, right? So you fold it over the y-axis right here. I keep drawing it back. You fold it over the y-axis right there, and then you fold it again over the x-axis right there. The graph would actually land right on top of itself. So this is an odd function because it's symmetric with respect to the origin. Okay, so that's how you can just look at graphs and identify them. Not too big a deal. Now, symmetry is really nice and easy to tell when something is even or odd. However, the calculation can be a little bit difficult, but I don't think it's too terrible. So let's look at this. So the way that you determine an even or odd function, like calculation-wise, is you do f of negative x, and you literally take negative x and you plug it in. And I get x squared minus 5, which is f of x. So you guys notice that this is saying that f of negative x is equal to f of x. This means even function, symmetric with respect to the y-axis because it's even, okay? This one over here, let's do this problem. Maybe I should split it up like this. Okay, so let's do this problem, G, and remember, you always use negative x to prove even or odd symmetry. So this would be negative x quantity cubed minus 1. So this would be negative x cubed minus 1. So now I'm going to factor out the negative. So this will become negative x cubed plus 1. Now think about this for a second. Is this function the same as this function? Right? Just with the negative in front. No, it's not. It would have needed to be this. It would have needed to be negative x cubed minus 1, because then this would have been negative f of x. But it's not. It's not that, so it's neither. It doesn't have symmetry with respect to the y-axis or to the origin because we couldn't factor the negative out and get the exact same function with just a negative in front. Let's take a look at this one. H of negative x equals 5 times negative x cubed minus a minus x. So this will become negative 5x cubed plus x. So when I factor the negative out this time, this is going to give me 5x cubed minus x. So now let's look. What does this guy represent? 5x cubed minus x is 5x cubed minus x with a negative sign in front. So this is quite literally negative f of x. Boom, it is an odd function. And it's symmetric with respect to origin. I don't want to write all that out. I'm running out of room. Okay, now let's do this last one. F of negative x, but this is an absolute value, so this becomes negative x, but you know that just becomes absolute value of, that just becomes x, and this just becomes, x. And also, if you're a little bit confused about this, the graph of absolute value of x looks like this. So it kind of looks like a parabola, right? But just a V shape. That is definitely symmetric with respect to the y-axis. So this is equal to the original, and this is an even function. Okay, so hopefully that gets you guys started. Remember, if you want to do it, you plug negative x in, you clean it up, and then you see if you get back the original, or if you can factor out a negative. All right. Okay, so this next part is we want to use the graph to determine local mins and local maxes. So what a local min or a local max is a local min or a local max is the highest point or the lowest point in that neighborhood, like in that location. So I always think of it as like the neighborhood I live in. You know, if you're the highest house in that neighborhood, you're the local max. If you're the lowest house in that neighborhood, you're the local min. It doesn't mean that you're the highest house in the whole city, but you're the highest house in that neighborhood. So that's just kind of the way I think about it. In calculus, we'll actually find local mins and maxes by doing calculations, but in pre-calc, we just use graphs normally, or sometimes our calculators to find it. So what is the places that there's a local max? So in their neighborhood, you have to kind of look. So I'm going to come over here, and I see right here, there's a neighborhood where there's a point on the graph that is lower than everything else in that area. There's a point on the graph here that is higher than everything else in that area. And there's a point on the graph here that's lower than everything else in that area. So that's what I'm going to look at for my local mins and local maxes. So right here, are all the values in this neighborhood right here lower or higher than when you plug in x equals -2? Well, I would say all the heights to the left and all the points to the right, I'm sorry, to the left and to the right of it are always going to be a little bit higher than whatever that height is. So I'm going to say I have a local max at x equals -2. Now, sometimes what they ask is they want to know, I'm sorry, that's not a local max. Sorry about that. That's a local min at x equals -2. Now, that also means right here, if I look to the left and to the right, all those points in that neighborhood will be higher than when I use x equals 2. So then I'll say x equals 2 is also a local min. Now, a local max is right here. So everything to the left and everything to the right of this is lower than that certain height. So we're going to say that that looks like when x is equal to 1. So we have a local max when x equals 1. We have a local min when x equals -2 and 2. Now, I want you to be careful of something. I believe sometimes they ask you for the x and y value. So then you have to give the actual point. Okay, so that means x is 1. And when x is 1, what does my height look like? That looks like about 3.5. Okay, when x is -2, what's my height look like? That's about 1.5. And when x is +2, my height is definitely 0. So that one is for sure. So these would be the locations of the absolute mins and maxes. So if they just ask you for the x value, then you just give them the x, but sometimes they want to know the height as well. Now, the difference between a local min and a local max and an absolute min and an absolute max is an absolute min or max is the highest point on the graph. There is nothing higher than it. And an absolute min, it is the highest or lowest point on the graph. There's nothing lower. So if we look at this graph right here, and we're going here, 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 and here, and here. What is the lowest point that graph will ever go? Well, it'll go right here, right? Right here at this location. That is the lowest point on this graph. So that's going to be my absolute min, and it's going to occur at 2. Oops, let me use red. It's going to occur at 2, 0, or x equals 2, or if they want just the y value, y equals 0. So the lowest point on this graph is 2, 0, or the lowest height is 0, okay? Now, if they want to know the absolute maximum, well, that's easy. Notice this graph right here, how high up does it go? It goes on forever because of these arrows, right? These arrows say it goes on forever. So when a graph goes on forever, up or down, it cannot have either a max or a min. You cannot say that your maximum is infinity, okay? Both of these graphs from both sides are approaching infinity. So we would say no absolute max, okay? Now, the other thing to keep in mind is when you're talking about local mins and maxes, in general, that means that you have to have two sides to a graph. So you wouldn't do this. You wouldn't have like a graph that's right here. Oops. Okay, let's say that this is at a height of 3. Let's say that this is 4. And let's say that this is 1, 2, 3, 4, 5, 6, 7. I don't know. Okay, 1, 2. Okay, so on this graph, you would not say that this is a local maximum, because, or here, you might be thinking, oh, but it looks like it's about to tail off and do that. Well, you don't know what's going to happen. So to be a local, it has to have a neighborhood to the left and to the right of it. It has to have something on both sides. So for our class and for calculus, local min / max cannot be endpoints. That's how I teach calculus as well. Now, I have seen relative mins and local mins. I have seen in one calculus book, sometimes they accepted it if there was like a particular way that you worded the problem. But in general, for us, endpoints cannot be locals. Local min and local maxes cannot be endpoints, okay? Even if they look like they might be the highest. Now, can an endpoint be an absolute min or a max? An endpoint can be a absolute min or max for sure. So in this particular case, we would say that there is 2 absolute maxes. It's at what does that look like? 0, 3. And the other point is 7, 3. So they both have a height of 3. That means that they're both the highest point on this graph. That means they are the absolute maxes. So you can have more than one absolute max, but they better both have the same y value. In this case, we do have a absolute min as well. So these are absolute max. And let me do absolute min. So the absolute min in this case, let's say that right there is 4. No, let's say that it's -3. So the absolute min in this case is 4, -3. That is the lowest point this graph will ever go. Okay, so x equals 4, y equals -3. Okay, now as it also turns out, we have a local min at 4 comma negative 3 as well. So a local min and an absolute min can be the same thing, right? So you guys see right here, this is the absolute min and this is also the local min right here. Okay, so it can be the same number, or sorry, the same location, but it doesn't have to be. So this is just something that get you guys started on your homework for sure. There's a little bit more, but I'll save that for the next video. I just want you guys to be able to have something to watch tonight before our next class meeting. Okay, that's going to do it for this video, guys. Talking about even and odd functions. Be sure to ask me for help tomorrow in class. Even and odd functions, people don't like them very much because it's kind of weird. Doing the calculations and stuff. But yeah, feel free to pick some questions from the videos or something you want to talk to me about tomorrow in the meeting. All right, that'll do it. Thanks for watching, guys.